Okay, I'm going to present this paper, Removing Double Logging with Passive Data Persistence in LSM-tree based relational databases, from this year's FAST. So in our seminars, we talk a lot about KV stores, but not so much about relational databases, even though since for a long time now, they've been we can say the backbone or something of a lot of enterprise systems. But typically they always have B trees at the storage layer, at least in the past. But now what we see is workloads are changing, to be write heavy, or as we read in the papers. And as we have now the emergence of LSM trees, we can claim that usually they're better for write heavy workloads. So what if we replace the B trees in these relational databases with LSM trees, which is starting to happen now. So, and as an example, we can look at MyRocks, which is Facebook's version of the MySQL thing, but they replaced the B tree with RocksDB. So typically it will look like this. So at the top, we have some sort of client program, and then that MySQL layer, which has its own interface for SQL queries and its own log. And then at the bottom, we have the storage layer, which would translate these SQL queries into key value pairs at the storage layer. And then at the storage layer, again, we have, for example, RocksDB, and then its own log. And in the diagram here, we have multiple column families at the bottom, or we can just say multiple trees. So with such a setup like this, maybe we can see the issue already. So at the top in the MySQL layer, we have a log, but we also have another one at the bottom in the storage layer. But the issue here is that the logs are fundamentally different in their purpose. So this MySQL log at the top just logs, called the bin log, just logs things like SQL statements with no actual key value pairs. And at the bottom, we have this RocksDB log, the while or the write ahead log that actually logs the key value writes in the data. So, well, we need these two logs to facilitate proper and fast recovery, or not fast, proper recovery. And two logs on the critical path for writes is just redundant and slow, as the paper claims. So the first thing we might think is, why don't we just use one of the logs, either or? So what we can do first is we can turn off the bin log at the top for the SQL layer. But the issue here is that the underlying storage layer won't know about the SQL statements that it has to recover. So while we can recover key value pairs, we can't really recover what we wanted at the top layer. In addition to this, typically the layer at the top, the log at the top will also be used for things like replication or synchronization. So if we turn off the while at the bottom, it can actually work, but there are a few issues. So first, if we turn off the log at the bottom storage layer, the guarantees about persistence become a little shaky. So for example, in this RocksDB setup, if we turn off the while, when a write goes to memory buffer, the layer at the top will say that it's complete. But as we know, these mem tables at the RocksDB layer are not flushed until later. So we don't really know if something is persistent or not when it will be declared persistent at the upper layer. And that's the main problem. We can, if we want, just remove the while and replay this log at the top from SQL, but it's prohibitively slow. So another scheme we might think about is, why don't we just internally commit after every, for example, n transactions at the SQL layer? Why don't we just flush the underlying store? Which does work, but it has two main problems. As we know from LSM stores, typically we want large sequential writes when we're flushing the tables. But if we keep flushing from the upper layer, we sort of break that design and reducing performance. And the second problem, which the authors claim is the most important problem, is that it breaks what we call design modularity. So the SQL layer at the top, or the database at the top, needs sort of detailed knowledge of how the storage works at the bottom. And we don't really want to break that. So in this paper, they introduced what they call passive data persistence scheme. And the ultimate goal here is to remove the while from the bottom and just rely on the log at the top, but provide all the same data consistency guarantees while we get the better performance. So when we remove the while from the bottom, we have these three main challenges in the paper. First, we call false data persistence, which I mentioned a bit earlier. So if we eliminate the while at the bottom, what will happen is that when we write something at the SQL layer in a transaction, it'll be flushed to the memory buffer initially, and RocksDB or whatever the storage engine is will return complete to the layer above. But at this time, the write is just in memory. There's no write ahead log. The second is called partial persistence, the second issue. And it applies if we have several column families or several trees in the same database at the bottom. So for example, in the picture, we have three column families, which we can just refer to as three LSM trees. And at the top, we have some transaction from the SQL layer that involves all three column families, so KV pairs in all three families. But the issue here is that writes may come to column families or trees at different rates, which means that the trees themselves are flushed at different rates. So even though we have a transaction that involves all three, two of the tables might be flushed, for example, and then we crash, and then one isn't. So we have this sort of partial persistence. The final issue is that if we remove the while, at least in this MyRocks setup, we lose what we call sequence numbers at the storage layer. And what we need sequence numbers for is like logical write ordering. So if we have two writes to the same KV pair, the first might get LSM1 and the second gets LSM2. And when we recover after a crash, we need to see LSM2 if we have already committed. But if we remove that layer in this case, we just lose this information completely. So the first part of their scheme, it's a two-part scheme, it's quite simple, but it works quite well. It's called the flush flag. So the key question is, if we turn off the while, how do we know what is flushed at the upper layer? So in their scheme, they have this special KV pair, what they call a flush flag, that's persisted at the end of each mem table flush, not at the end of each transaction or commit. So the key is just some magic number, 128 bits, and the value contains two things. So it contains the sequence number of the last transaction for this mem table and the logical sequence numbers of the first and last transactions. And basically on recovery, what we can do is we can read this flush flag and see the latest transaction that was persisted and the sequence numbers that belong to that transaction. So the second part of the scheme is called, well, there's two parts, but I just combine them, Epoch-Based partial recovery. So when we crash and we want to recover the database, we just read the flush flag for every tree. But the issue here is that, as we explained earlier, the trees might flush at different rates. So now, for example, for each tree, we have the last transaction for this tree that was made persistent, the sequence numbers of that transaction. But yeah, as we described, the transaction might have writes in other trees. So while we have a local recovery point for each tree by reading this flush flag, what we do is we make a global point, which is the earliest transaction we need to recover using these flags. So I'll just demonstrate it here. So in this diagram at the top, we have TSN, which means transaction sequence number. And in the diagram, they're just in letters. So we have transaction M, N, S, and T. So what we can do in this scheme is we'll read these flush flags from each column family, so each tree, CF1, 2, and 3. And we'll notice that CF2 was the slowest, so it only flushed up to transaction N. And a naive solution is we could just replay from transaction N to T from the upper layer and recover, but it could be a lot slower than it needs to be. So they introduced this scheme called partial recovery, where we can recognize that the global point of recovery in this scheme is, in this example, is transaction N. But we can also recognize from column families 1 and 3 that their local recovery points are T for column family 1 and S for column family 3. So we only need to replay from transaction N for column family 2. And for column family 3, we can just replay from transaction S. So this is what they call partial recovery. And that's it for the scheme. It's very simple, only 500 lines or so. And it was only 2 pages, I think, in the paper. So they implemented as a modification of MyRocks, and they compared against MyRocks in the paper. So in this paper, they test with LinkBench and TBCC2, not YCSB or something. So the 2 main questions we want to see is that, given that we can remove the while, how good is the performance, in normal workloads, but also how does the recovery speed compare? So if we look at the LinkBench performance in these tables, on the right we have the improvement, and then we have the MyRocks and the PASP performance. And the table on the left is the general performance for just the loading phase, and on the right it's for the query phase. So for the loading phase, where it's pretty much just write only, and we see a massive improvement in the performance just because we could remove the while. So now with the storage layer, we're not persisting every single write synchronously. We're just waiting until the main table is flushed later. Whereas in MyRock, since the while is turned on, performance drops, as we know. And the same trend we can see in the query running phase, though the performance improvement is lower because there'll be some reads there. It's not just total writes. So earlier we talked about what could be an active approach where we just flush every n transactions or something and then recover from there. So we can check the performance versus that. And at the top, if we look at the recovery time, we have the PSV scheme on the left, and then active 100 to 2000. So this means we flush the underlying main tables every 100, 300, etc. transactions. And while it can be good, for example, if we're flushing every 100 transactions, the recovery time can be very fast because we only need to recover, between 0 and 100. But if we look at the bottom, the throughput graph, quite a big difference in throughput, because when we flush all the time and flush very frequently, we're sort of breaking that LSM-tree performance benefit where we're flushing large writes all the time. And another bad thing about flushing all the time is also that if we flush a lot of small tables, we're pushing tables down the LSM-tree, so we're just compacting or reducing performance. And finally, we can look at the performance with TBC. But in this graph, in this slide, we also compare it to what we call a naive scheme, which is just turning off the while in RocksDB with no other changes. So we can call this the best case or ideal performance. But in this case, we have to, even though the performance is great, we have to replay the entire log on recovery, which is slow. So if we look at the bottom graph here, if we look at the top table, and we can see that the performance of PSV, it's almost identical to the naive scheme. So we can claim here that PSV is giving us best case performance. But if we look at the bottom graph for the recovery, and for the naive scheme, it just keeps getting slower and slower as we fill the database with more data. But for PSV, the recovery time, it's not always the same, but it stays very low, and because we don't need to replay the entire log. So to conclude, we have this double logging problem in these relational database systems, when we use an LSM store underneath, or any other type of store. But the naive solutions either perform poorly in performance or recovery, and they don't really have good performance in both. So they introduced this thing, PSV, passive data persistence scheme, that only required small amount of modifications, but we could say we have best case performance and very fast recovery. Thank you.